In this video, I will walk you through how to configure a topology optimization with MC Nastran SOL 200. Now, the goal of this optimization is to minimize the mass while constraining both the stress and the first natural frequency. And on this slide, I have an idea of what the final result is going to look like. Here on the left, this is starting geometry. Basically, we want to either remove or add material to the golden section of this part. I did three different types of optimizations. One optimization involved a topology optimization with a maximum von Mises stress of 100 megapascals. This yielded very little mass savings. So what I ended up doing in the second topology optimization, I increased the maximum von Mises stress to 200 megapascals, and this led to a mass reduction to approximately 6.5 kilograms. And then just to show you something different that you rarely ever see, a shape optimization. So I went ahead and used the Nastran optimizer to configure a shape optimization. Here, ultimately, we had a mass reduction to approximately 13.5 kilograms. Topology and shape optimization each have their benefits or rather advantages and disadvantages. So I wanted to show you what it looks like when you configure either one. Now, this video was inspired by a set of questions I received from a viewer. Here on the left, I have the questions that were asked. Number one, how do you create a hex mesh for Nastran? So this is covered in a separate video. So I think I will link it in the video description below. The next set of questions were regarding how to set up a topology optimization. Here, the goal was to configure an objective that minimized the weight. The goal was to make sure that the maximum von Mises stress did not exceed 100 megapascals. I should mention that when you're dealing with von Mises stress, the equation has a square in it, so you're basically dealing with only positive values. You won't be dealing with negative von Mises stresses. They're all positive for the most part. Number four, how do you configure a SOL 103 modes analysis? So here, this makes the process a little bit more complex, but I'll show you how to set it up. You want to constrain both stresses for statics analysis and natural frequencies for normal modes analysis. And then the last question, can I actually constrain the stress of 3D elements? The answer is yes, but you have to be careful. And I'll go into this in a few moments. So, stress constraints. If you are dealing with topology optimization and you're creating top bar entries, you will use the stress field to create your limits on the von Mises stress. If you try to use the DRES1 during a topology optimization, this is not going to work. So I wanted to make that clear. Now, on the other hand, if you were performing a shape or size optimization, then that's perfectly fine. You can go ahead and create a DRES1 to use the stress option, the P-solid option, and item code 13. So again, if you're using topology optimization, and you want to constrain stress, you have to use the stress field on the top var entry. If you're performing shape or size optimization, you can use a regular DRES1 entry, configure it to use the stress, and so on and so on. Now, this item code, this is very important. When you're dealing with an element, like a 2D C-quad 4, a tetrahedral element for a 3D case, each element is going to output a lot of data. So I'll give you an example. For a hexahedral element that might look something like this, there are 8 corners and 1 center point. So here in the middle is the center. Here might be a grid point 1 and grid point 2, and so on and so on. If you take one of these points, you're going to get a lot of data. You're going to get the normal stress along the X, the normal stress along the Y, the normal stress along the Z, and then shear stresses for each of the planes, if you will. You're also going to get a principal stress and a von Mises stress and a few other pieces of information, and this is just for one point. I'll call it GI. Now you're going to have in total 9 points to output data for, 8 corners and 1 center point. So for a hexahedral element, you might be outputting anywhere from 100 to 200 quantities. If we look in the F06 file, here we have a table of the stresses in hexahedron solid elements. There's a lot of data. The first few rows are for the center of the element. The next few rows are the stresses for the first corner, if you will. The next few rows are for the second corner rather. And then here I've truncated some data just to keep this clean, but you also output data for the remaining 6 corners. So here in total, there could be 27 rows of data. But here I'm only displaying a fraction of the number of rows. So here, if you look at each column, or rather each value here has a different item code. For example, the normal X stress for the center, this has item code 6. The shear stress has item code 7. The principal stress has item code 8. Then you have item code 9, 10, 11, and so on and so on. You have item code 12. And then at the far right hand side, this is the von Mises stress for the center of the element, which has item code 13. The next row, let's go ahead and use blue. I believe the next value here, 2.2, this is going to have item code 14, and then the numbering is repeated. So this next value is item code 15, 16, 17, 18, 19, and so on and so on. So this is repeated until the very final value. The item code at the end is item code 193, and it corresponds to this value in the table. So here, all we're interested in item code 13, which is the von Mises stress at the center of the code element. If you look in the MSc Nastran Quick Reference Guide, there's a chapter called Item Codes. This has a listing of every output from each element. And here we look at the C hexa. For the most part, the item codes for the first 13 are the same for C penta or pentahedral elements or tetrahedral elements. So for all these 3 elements, we can just use item code 13 and you're going to call out the correct response. You're going to constrain the correct response for the optimization. Now, today we're going to be using MSc Nastran 2024 or 2022. I forget which one. But my recommendation is to use MSc Nastran 2017 or newer. That's because starting in this version, you can output the H5 file that contains the stresses and the displacements. So that's why we're using MSc Nastran 2017. And now a quick overview of the topology optimization problem statement. We're just going to modify the material in the interior of this bracket. We can either add or remove material. Since this is a topology optimization, it's better to constrain, or rather to work with the fractional mass. This bracket has an initial mass of 18 kilograms. So let's go ahead and erase this. So as an example, suppose at the end of the optimization, the final mass is 9 kilograms. The fractional mass at the beginning is 1.0. 18 divided by 18 gives you 1. And then at the end, it's 9 kilograms divided by 18 kilograms. So the fractional mass at the end would be 0.5. So here we are going to be dealing with fractional mass values. Now, the constraint. Recall that the constraint is defined directly on the top var region. So X1 is going to be a top var entry. So here on the right, this constraint is actually going to be defined on the top var entry. The first natural frequency here on the bottom right, we're going to create a DRESP1 entry, and we're only going to constrain the lower bound. We want to say that this natural frequency should be greater than 200 hertz. The original question asked to constrain the natural frequency between 200 and 400 hertz. In a majority of cases, the first natural frequency has a lower bound, but no upper bound. So we are going to ignore the upper bound. If you really wanted to, you can add an upper bound to the natural frequency. Now here on this next slide is the problem statement for the shape optimization scenario. So we're going to define one shape region that's going to either contract or expand. So these dotted lines represent what the shape looks like when it's being contracted. And that's what we're going to configure later on in this video. Since we're no longer working with a topology optimization, we can just work with the regular weight or mass response. Here, instead of defining a top var region, our stress constraint is going to be defined with the DRES1 pointing to item code 13. And then for the natural frequency, that's going to be the same as before. Now, you might be asking, why am I using 100 or 200 megapascals instead of 100 megapascals? The reason is the following. When I tried 100 megapascals as the upper limit for the von Mises stress, it only removed a small amount of material, as you see here. It's not significant. So I thought, you know what? I want to make a really interesting and exciting tutorial, so I increased the limit. And this is the result. A lot more material was removed. This solution is a little bit more interesting. So we are using 200 megapascals as the upper limit for the stress today. And so, okay, let's go ahead and jump back to that slide and see what else we have. And so on the next slide, just a procedure of what we're going to do. Okay then, so I'm assuming you have access to the Sol 200 web app. Let's go ahead and jump to the topology tutorials section and download the bulk data file for today. Now, there are some modifications we have to make to this bulk data file. The first one is the following. We have to add a third subcase. Now, the third subcase is going to be used to perform the normal modes analysis. So here, let's go ahead and add subcase 3. We're going to use the same constraints or boundary conditions. So here we fixed some of the holes, we clamped or fixed the holes, and we're going to call out, we're going to point to those constraints with SPC equals 2. And now we need to tell Nastran how to extract the eigenvalues. So here we're going to say method equals 101. This is going to point to this entry, EIGRL. So this is going to trigger the use of the Langshos eigenvalue solver. Here we're going to give it an identification number 101. We're going to say use the Langshos eigenvalue solver to get at most 20 natural frequencies. Let's go ahead and save that. And let's go ahead and write out a new bulk data entry, HDF5 out. So this is going to trigger Nastran to output the, the H5 file. And then another bulk data entry, param grd pnt. This is going to trigger the output of the weight in the F06 file. So again, this helps with eigenvalue extraction. HDF5 outputs the H5 file, which contains the stresses, displacements, and all the other results. And param grd PNT outputs the weight. If you look in the F06 file, you get this big table output from grid point weight generator. If you look at this first entry, this gives you the mass. So this is about 18 kilograms. So initial mass is about 18 kilograms. So we'll be using that throughout this exercise. Okay then, one other thing, and this is the very important part. Remove this case control command, smethod element. This conflicts with the shape optimization. This causes some user fatal messages. So we are going to remove smethod equals element. Actually, here, let me do this. Let me just completely delete it from this exercise. And once you've made these modifications, make sure to save the file and we're ready to go. So let's go ahead and jump to the optimization web app. This is where we're going to configure the topology optimization. So let's go ahead and upload that bulk data file. Let's go ahead and jump to the topology section. Click on P-Solid1 to set it as a topology design region. Click on options, turn on the stress limit column. This is where you supply the upper limit on von Mises stress. So here we're dealing with newtons, Pascal, meters, newtons, Pascal. So here I type in 200 times 10 to the 6 for pascals, or 200 megapascals. And we're dealing with both the topology variable and the stress limit. Let's go to objective and look for fractional mass. Here we want to minimize the fractional mass. Let's go to settings. Here, let's go ahead and limit we'll leave this as the default. Let's go to the exporter, and I forgot to do something. If you go to constraints, I forgot to define the natural frequency constraint. Change the responses to normal modes. Type in frequency, click on frequency to create one constraint on natural frequency. In this box for ATTA, you can specify the mode number. If you want to constrain the natural frequency for mode 25, you type in mode 25. If you want to constrain the natural frequency for mode 13, you type in 13. But here we want to constrain the first natural frequency, so we type in 1. And the lower limit is 200 hertz. In the subcases section, click on options, click on multidisciplinary optimization. For the third subcase, it's a normal modes analysis. Subcases 1 and 2 are statics. And in the third subcase, we'll take the natural frequency, mark the checkbox for subcase 3, and now we've assigned natural frequency constraint 1 to subcase 3. Go to the exporter, click download PDF files, and we'll go ahead and get a new set of bulk data files. So let's go ahead and rename this. Let's go ahead and extract the contents. Let's go ahead and make sure we have the following. So the top bar has the stress limit imposed. We're minimizing the fractional mass. We're constraining the first natural frequency to be greater than 200 hertz. So let's go ahead and start this topology optimization. Okay, so let's go ahead and look at where we're at right now. Okay, so let's go ahead and open a few web apps. So let's go ahead and open the viewer web app and the responses web app. So in the viewer web app, we are going to use this web app to look at both the shape optimization results and the displacement and stress results. In this case, we don't care about displacements, we care about the mode shapes. So we'll be looking at that in a moment. So let's go ahead and see where we're at. Now this optimization is going to take a few moments, so I'll go ahead and pause here. Now, while this topology optimization is happening in the background, let me talk about one setting here, the maximum number of design cycles. So here, let's go ahead and make a plot. So here on the vertical is the number of design cycles. So at the beginning, we have design cycle 1, design cycle 2, and this would continue on. Maybe you can have up to 100 or 200 design cycles. Here in the vertical axis is going to be the objective, which in this case is going to be the fractional mass. Now, what tends to happen is the following. Your objective might be up here. It might start here. During the optimization, it will quickly converge, and then it will level off. And then you have almost like a convergence. But the optimizer will keep running, but will make very little improvement. So all of this is yielding no improvement. So what you can do is the following. You can say, you know what? Terminate here. At 50 design cycles, stop the topology optimization, because I know you are not going to make any more progress. Most of the improvement has been made within the first 50 design cycles. So that's why instead of using maybe 100 or 200 design cycles, I know that in most cases I can just stop at 50 and I've already obtained most of the improvement. Okay, so let's go ahead and see where we're at with the topology optimization. I see it's still, I think it might actually have finished. So this gives us a few more moments to complete. Okay, perfect. So it's pretty much done. It's going to open a bunch of results pages. So before we talk about the results, there are a few things we need to inspect. The objective. Did we minimize the objective? Number 2, is the final design feasible? Did we satisfy all the constraints? So now let's talk about normalized constraints. So we'll let Ri represent a response. It could be a stress for element 1. It could be your natural frequency. You might have an upper bound, and then you can have a lower bound. What internally happens, this is converted to normalized constraints. So even though I have a lower and an upper bound here, internally these are normalized. So then for this one definition, I get 2 normalized constraints. But then it gets more complicated. So suppose this is response 1, then I have response 2, response 3, response 4, and so on until response 100. So in this case, I could have 100 normalized constraints for the lower bound, and then another 100 normalized constraints for the upper bound. So in total, I could be dealing with 200 normalized constraints. What the optimization procedure does, it takes the maximum out of all 200 normalized constraints and it reports it once. So if we look here at the results, the first question, did we minimize the objective? The answer is yes. We did minimize the objective. The second question, do we have a feasible design? If we look at the beginning for the initial design, there's only one normalized constraint reported. This is the maximum normalized constraint. So this, again, is the max out of all normalized constraints. That is what's being reported here. So we take the lower and the upper bound, we normalize it, so G1 and G2 and so on to G200 in this case. Each bound gets its own normalized constraint. And then at the end, we take the max out of all the normalized constraints, GI. And that's what's reported for each design cycle here in this plot. Now, if we look here, the initial normalized constraint is negative. Great. If it's negative, that means you're satisfying all of your constraints. So I'll give you an example. Here it's negative 0.299. Suppose that the stress normalized constraint is negative 0.299. And then the natural frequency normalized constraint is, I don't know, negative 100. If you take the max, negative 0.299, negative 100, guess what that is? It's negative 0.299. And that's what we get here, negative 0.299. Okay then, so far for the initial design, it's negative, so it's satisfying all the constraints, and then it goes to positive. Here, it's actually violating the constraints for design cycles 2 through about 10. And then after that, it's kind of jumping up and down between violation and satisfaction. And then here towards the end, we actually get a negative normalized constraint, which is good for us. It's indicating we're satisfying the constraints. Okay then, so now you might be interested in seeing what these normalized constraints correspond to. These normalized constraints do not have units, but you want to look at units of stress or hertz. if you look in the responses web app, you can upload the F06 file. So let's go ahead and do that. Let's click on maximum constraints for each design cycle. Remember that at the initial design, the maximum normalized constraint was negative 0.299, which is here in this row, in this column. Now for the final design, we get negative 0.01. And if we look back at this plot, guess what we have? We have negative 0.01. So if we look at the column called label, this tells us which response it corresponds to. Here, it's corresponding to GL stress. When you go ahead and define the top bar with the stress field, like we did in this example, this outputs the so-called, I believe it's called global stress, GL stress. So this is telling us that, hey, the worst case constraint so far is the von Mises stress constraint that was configured. And now we need to confirm this. So what we're going to do is the following. We're going to take the H5 file and we're going to upload it here. And in a moment, we're going to look at the stress results. So let's go ahead and select the stress data set. Let's look at the first subcase. We'll go ahead and mark this checkbox. And this is saying select subcase 1 for design cycle 0, which is the initial design. Let's go ahead and turn off the deform shape. Let's go ahead and select von Mises stress. We're only looking at the data for the center of the element. Let's go ahead and identify where is the highest stress. So here is the highest stress. One thing we did not do, let me redo this here, or I'll actually skip it. Remember that we only constrained the stress for P solid 1. Or actually, no, let me take that back. When we define that stress constraint, it applies to every hexahedral element in the model. So this is what the original stress was, 140 megapascals. Let's go ahead and jump to the final design cycle. We want to make sure that the mass is less than 200 megapascals. Okay, so here is the final result. Okay, perfect. So here we have 180 megapascals, which is less than 200 megapascals for subcase 1, which is okay. So looking good so far. Let's look at the second load case. So here we're going to select subcase 2 in the subcase column. Here we're going to look at design cycle 50, which is the final design cycle. Let's mark that checkbox. We're going to pull the stress results. And let's go ahead and display the label for the maximum stress. Where is that located? So that's here in this hole. And here the result is about 186 megapascals. So 186 megapascals, which is less than 200 megapascals for subcase 1 or 2, which is okay. Now let me double check one thing. Was it 180 for that one? I want to make sure it was 180 megapascals. Let's just go ahead and look at, see what it was. Oh, it was 182. So we zoom out, it's 182, about 183. So maybe I'll use 183. Okay, perfect. So this was 183 megapascals, which is less than 200 megapascals for subcase 1. That's good, that's okay. For the second subcase, or the second load case, we get 186 megapascals, which is less than 200 megapascals, which is also okay. So the stress constraints are good so far. Let's go ahead and look at the first mode shape and its respective natural frequency. So here we want to know this for subcase 3, which is the normal modes example or load case. Here, let's look at mode 1 and mark this checkbox. And here we get a very exaggerated mode shape, and that's because the scale factor here on the right is very high. Let's reduce that to 0.1. Let's go ahead and fit the model again. Okay, so this is what our first mode shape looks like. If we wanted to, we could turn on and off the shape. So this is what the first mode shape looks like. What about the natural frequency? Now, when you look at the natural frequencies, you get this row, which is the eigenvalue. The eigenvalue here is about 3.2 million. But if you look in this next row, we get what the natural frequency is. It's actually 284 hertz. So if the lower bound was 200 hertz, but our actual natural frequency is 284, great. We're satisfying the constraint on the natural frequency. Now here, let's do one thing. Let's confirm this. Let's go ahead and look for that table that lists the natural frequencies. So here, this first table on line 390, these are the natural frequencies for the initial model before optimization. On line 11,200, this is a new set of natural frequencies for the optimized model. You can see that we get a natural frequency of 284 hertz, which aligns with what we see here on the screen. So perfect. What we have in the F06 file aligns with what we see in the viewer. Now, so far we've confirmed the stresses and the natural frequencies. Now let's look at the topology results. So here on the left, bottom left, I turn on the topology panel. Let's attach the model.des file, which contains the results of the topology optimization. Here on the filter, I typically use a threshold of about 0.3 or 0.4. If we rotate the model, and here is the original model, and this is after we filter, we remove elements that are not critical to the solution. And so this is what the result is. I am now going to download an STL file. So I click STL download, and on my desktop, I now have an STL file. What I'm going to do now is I'm going to walk you through how to update the final geometry. Our final geometry looks like this. But now we have to update the geometry. We have to remove material from the actual geometry. How would you go about doing this? Now, my recommendation is to use a dedicated CAD program to this. Here are some examples of what the CAD programs are: AutoCAD, Solid Edge, CATIA, so on and so on. What you would do is the following. You would import the original CAD of your bracket in this case. So let's go ahead and do that now. Right click, import model, parasolid. Let's go ahead and change the units. Let's go ahead and change that to meters. Yes. Let's go ahead and find the parasolid file. So this is the original CAD geometry that you see here. Let's go ahead and create a new group. And let's go ahead and import the STL file. So the STL file has a bunch of triangles that represent the topology solution. So here Patron is doing its work. Let me do this. Let me change this into wireframe. Let me go ahead and clean this up a little. Okay, perfect. So here you can see the profile of the original CAD geometry. So here you can see both of them are superimposed. What you would do in the CAD program, you would use CAD to manually modify the original geometry. So you would remove the unnecessary material, the material that's not critical to the design. Towards the end, you should get something similar to this, but it should be smoother and more professional looking. Here, let's go ahead and jump to an example online. So let me find that example real quick. I think it was this example. So here on the bottom left was the original mesh, or the original geometry, if you will. Here in step number 2 is the geometry. we got from the topology optimization, but this is unusable. The mesh has lingering elements. The mesh is not smooth. You cannot use this mesh for anything. What you do is you go into CAD, you superimpose your original CAD with the STL file, and you use that to help remove material. So this is a very time-consuming process, so I am not going to show you what the process looks like exactly. Also, I do not have a CAD program on my desktop. I typically outsource this CAD work to a separate individual that knows CAD. So again, other CAD programs such as AutoCAD, Solid Edge, CATIA, and so on and so on, they're useful for that. Now, you might be tempted to use one of the following preprocessors: VMAP, HyperMesh, ANSYS Workbench, Patron, MCA Apex. You might be able to update the CAD in some of these programs, but in most cases, it might be too difficult or it might be too time consuming. So definitely consider using CAD to modify the CAD. Okay then, so like I said, use CAD, polish up this topology solution, and when at the end, you would go ahead and perform a final FEA to make sure that the final design also satisfies the stress and the natural frequencies. Okay then, so let's go ahead and close some of this because we're pretty much done with the topology optimization. Now, let's go ahead and talk about shape optimization. So here, let's do the following. Let's delete the topology variable. When we delete the topology variable, we remove the stress constraint, so we have to re-add it. Let's change this to statics and look for stress. Let's turn on stress here. Say we want to constrain the stress for any element associated with P-solid 1 and 2. If we look at the original document, we have P-solid 2 in green, P-solid 1 in yellow. Here we want to say that the maximum von Mises stress should be no more than 200 E6, and then the item code. That's item code 13, like we explained a moment ago. Subcases. Let's take that stress constraint, assign it to subcase 1 and 2. Let's go to the exporter and export this. You'll notice one thing that's missing. There are no design variables in this example. So we'll add those in a moment. We'll call this to shape. We'll extract the contents. And we'll go to the viewer. So let's go ahead and open the viewer again. Let's go ahead and import those new bulk data files. And let's go ahead and jump to the shape panel. In the shape panel, this is where you can configure the shapes for the shape optimization. And really quickly, let's go ahead and click on Add Shape. Let's click on this Edit tool. Let's go ahead and select a few elements here. Now, these elements are either going to expand or contract. And here, let's go ahead and click on Run MSC Nastran. This is going to generate a preview of the shape. So let's go ahead and type in maybe 0.5. So this test delta y, this lets you experiment with various changes in the shape. Now, this is very useful because if the change in the shape variable is very high, it's going to distort the mesh and it's going to cause a failure during the optimization. So here is a very distorted mesh. We never want to let that variable reach 1.01. But here, when we experiment with 0.01, this is a little bit more manageable. And here, let's test 0.05. And this is what that shape looks like. We'll say, okay, 0.05, maybe I'm not that comfortable with it. Let's try 0.02. Okay, I'm more comfortable with this maximum change. So I take that change and I paste it here in the upper bound of the shape variable. So here, delta y upper bound is now 0.02. Now, let's go ahead and do this now. Let's go ahead and increase this picking sphere. It might be a little too big, so let's go ahead and do this. Let's go ahead and drag and select all these other elements. Now, I'm not actually going to expand all of the elements, so let's go ahead and deselect some of these. Okay, perfect. So let's maybe zoom in a little. Let's go ahead and deselect these elements. These elements are going to remain constant during the shape optimization. Just go ahead and deselect these elements. And then we're also going to repeat this for the opposing side. So let's go ahead and select as many elements as we can select here. Okay, perfect. So we'll do the other side in a moment. Here, like before, let's go ahead and deselect some of these elements. Now, in more complex scenarios, you will have multiple expand and contract regions. But here, I want to keep this exercise simple. I want to show you what the shape optimization process is, so that's why I'm going over it right now. Okay, then let's go ahead and focus on this other side. So everything in gray is not going to change, but everything in yellow will change during the shape optimization. So let's go ahead and do this. Let's go ahead and rotate this a little bit more. Okay, let's go ahead and select this here. Okay, now let's think about selecting these elements to change. Let's go ahead and delete these ones here. Okay, let me make sure everything looks good here. Okay, now let me rotate this. Let's go ahead and continue the process. We're going to deselect. Let's go and rotate this. Okay, so I want to, whatever is happening at the top, I want to make sure I emulate here on the bottom. Okay, perfect. So let's work on this region here. Okay, so let's go ahead and deselect some of these elements. Let's rotate this. Deselect again here. Let's rotate this. Let's go ahead and deselect these other elements. And you know what? I'm feeling a little daring, so let's go ahead and select these elements here. Whenever you modify shape, whenever you add elements or remove elements to the shape, be sure to rerun MSC Nastran to generate the preview. This is very important when it comes to formatting all the bulk data entries. I'll explain that in a moment. So here, let's go ahead and deselect these elements. And let's go ahead and deselect these last few elements. Okay, so let's click Run MSC Nastran. So a quick comment about this. If you're using the professional version of the Sol 200 web app, preview works. If you're using the free trial, preview does not work. So keep that in mind. I know some of you are students who are using the free trial. If you're trying to replicate this example, preview is not going to work. You need to have the professional version where you download the installer and install it on your own desktop. Okay, then let's go ahead and look at the preview. Let's go ahead and make sure the test value here is a little bit more manageable. Okay, so right now we're looking at the shape when it's being expanded. And I'm just glancing at it, making sure nothing is too distorted. Okay, this looks okay. And now let's go ahead and contract this by negative 0.03. Now the question is, does it look distorted? And when I look at this, it looks okay. Now let's go ahead and reduce this a lot more. Let's try negative 0.05. Okay, the elements do not look distorted. One option here is the look inside option. These are not triangular elements. They are not tetrahedral elements. This is just a representation of the outer boundary that's being changed. You can actually use this to look inside. And if you spot any distorted elements, then you should go ahead and fix them. Let me give you an example. Let's go ahead and suppose we change the test value to delta y equals negative 0.15. And if you look here, and let's look inside, from the outside, we know we distorted the mesh. Look at all these elements that are going through each other. This is going to fail during the shape optimization. When you try and look inside of this, you can no longer look inside. So that's how you would use the look inside option. So let's zoom out. Let's go ahead and adjust delta y to negative 0.05. So if at the least the shape changes to negative 0.05, you will most likely not get a mesh distortion. So we are going to take this confirmed value. We are going to use that as the lower bound for the shape variable. Now what I can do is the following. I can go to the new entry section. Here I get a summary of all the changes that are being done to the bulk data file. All the other lines are being left as is. Nothing is in most tools, what happens, the tool will modify every line, which is problematic because then you have to struggle and stress out that, okay, now every line's changed, have to make sure every line is correct. Here, we do not touch the other lines. We only touch a few lines. So if you go back to the new entry section, let's go ahead and count. So this is line 1, line 2, 3, 4, 5, 6, 7, 8, 9. And then here, I'm estimating this is about 50 lines, maybe 100 lines. So at most, we're modifying only 60 lines. All the other lines in the bulk data files are left as is. So right now, let me pause the video and let this file download. Okay, now that we have the new zip file, let's go ahead and take that zip file. Let's go ahead and rename it. Go ahead and extract it and then start the shape optimization. Okay, now while this is happening, let me explain why it's important to run MSC Nastran each time you add or remove elements to a shape. Inside of this file, design shapes psolid1, there's this entry, dvb shape. In field 5 is a scale factor for the shape. This scale factor is very important for successful shape optimization. Now, when you click on Run MSC Nastran and it computes the shape, the web app automatically determines the best scale factor to use. So that's what I mean before when I said make sure to run MSC Nastran to create these shapes so you can have the updated scale factor here in the bulk data file. Okay, let's go ahead and look at the results. And here we had a failure. So let's go ahead and look at the failure message. If you go to the very end, we should be able to see what the failure message is. Okay, so here I made a mistake. In the optimization web app, let's go ahead and see what that was. Right, here what I was supposed to do, I was supposed to remove the old fractional mass and I was supposed to add a weight objective. So now, instead of going through the whole process of recreating this, let me just copy this entry from the right Let's go here, open this. Let's go ahead and paste this. So here we have the new entry and then the old entry. Let's go ahead and delete that and save it. Let's go ahead and delete the old result files and restart the shape optimization. So here, if you look at the message, user fatal message, and this was the old one, DRESP1 with R-type FR mask cannot be used for sizing or shape. This was my mistake. That's okay. We went ahead and corrected the mistake. So we'll see where we're at with this new optimization. So let's go ahead and look at the results. Okay, perfect. So here we get the results of the optimization. We're still not complete or done, but it's good to see that the optimizer is actually doing something. Let's go ahead and see what we have at the end. And I just heard the beep. That tells us the optimization is complete. Okay, perfect. Did we minimize the mass at the end of the shape optimization? The answer is yes. Our new mass is 10.43. So let's go ahead and document that here. Actually, I did not document the topology optimization mass. So we'll do that in a moment. Shape optimization gave us 10 kilograms, I believe. So let's look here. We have 10.43 kilograms. The bigger question is, do I have a satisfied design? We started off with negative 0.32. We have 0.27 or 27% violation. Here we have a very small normalized constraint value. So this is good. This is telling us that the optimization yielded a feasible design, one where all the constraints are being satisfied. So now let's continue on. So now let's go ahead and look at the optimized solution. So in this other directory, workspace B, we have a modeled final BDF. This bulk data file has the updated mesh. So if we import that, I'm using the wrong window here. Let's go ahead and upload that new bulk data file. And all the nodes have been updated to yield the new optimized mesh. So let's change the color. Okay, perfect. Now the bigger question is, what are the stress results? Are they all within 200 megapascals? So let's go here, select the H5 file and import it. And let's go ahead and look at the stress results for subcase 1 for the final design. Let's go ahead and make sure that's no more than 200 megapascals. Let's go ahead and turn off the deform shape. The scale factor is too big, so I don't want to deal with that right now. Let's go ahead and turn on the label, and perfect. Look at that. The maximum von Mises stress is right at the upper limit of 200. So subcase 1, 200 megapascals, which is less than or equal to the upper bound of 200 megapascals. Now subcase 2, what does that look like? Let's go ahead and write some notes here. Let's go ahead and switch to subcase 2. So here, let's go ahead and select subcase 2 in this column, select this checkbox. Let's pull the data from the H5 file. And let's go ahead and turn on the label and try and identify where exactly is my highest stress. So the highest stress here is 166 megapascals, 166 megapascals, which is less than 200 megapascals. Okay, so things look good so far. Let's take a look at the first eigenvector or mode shape. So we'll select the eigenvector data set. We'll select mode 1 and the last row, which is the last design cycle. And let's go ahead and adjust the scale factor. So 0.01. Okay, so this is what our bracket looks like. Maybe let's go ahead and turn on and off the eigenvector. And let's go ahead and increase the scale factor a little more. Okay. So this is the mode shape. And let's look at what the natural frequency is. Perfect. It's 334 hertz. Subcase 3. So remember that the lower bound was 200 hertz, and then our new natural frequency is 300 hertz. So perfect. The design is feasible. All design constraints are satisfied. Perfect. So that's the end of this shape optimization. There's one more step actually. You want to update the CAD. Like I said before, take the original CAD, superimpose it with the updated mesh in this case. So you would have this mesh, overlap it with the CAD, and use this solution to remove and guide the process of material to remove. Now, one other thing, let's compare this to the topology optimization. Now, sometimes the shape optimization will yield a better answer. Sometimes the topology optimization will yield a better answer. In most cases, the topology optimization will yield a better answer. Here, let's go ahead and look at what the final result was, 0.23. So 18 kilograms times 0.23. Or here, let me look at this. Okay, so maybe this yielded a better solution. Okay, so here we have 4.14 kilograms. Oh, okay. So in this case, the topology optimization yielded a better mass savings. Topology optimization produced a design that has 14.14 kilograms of mass, but shape optimization yielded a heavier solution with 10 kilograms. So we're pretty much at the end of this tutorial. Let me go ahead and see if there's anything else to cover. Nope, I think I covered everything I wanted to cover. Here, just to quickly recap, you saw me perform a shape optimization here. That was feasible. The stresses were within the maximum von Mises stress value. The natural frequency was within the constraint tolerance that we specified. I also performed a shape optimization where, again, we had all the stress constraints were satisfied and the natural frequency constraint was also satisfied. And the last thing I'll leave you off with is my contact information. So just in case you have questions, it's always helpful to have somebody to consult with, to ask questions regarding what's the best way of doing it. You're more than welcome to contact me at this email address. I'll get back to you as soon as I can. And that's pretty much the end of this video. So as always, thank you for watching, and I'll see you in the next video.